Thank you, the rest of the organizers, for giving me a chance to speak, and especially I'm grateful for giving me a reasonable time, compatible with my time zone. It's nice to see many of the familiar faces that I haven't seen in over a year. Not the same as a real conference, but better than nothing. So in this talk, I want to look at the magnetic materials from a quantum information perspective. The motivation is quite basic, and much of what I'm going to say is going to be quite elementary. So please don't feel insulted with me stepping through some very elementary aspects of quantum entanglement in magnetic materials. It's a topic that is relatively new for us, so please feel free to be critical and give us constructive feedback. So here's what we're motivated to do. I mean, let's consider some generic magnetic material made up of a bunch of spins, which are fluctuating at a very high temperature. So at very high temperature, the material is paramagnetic with no entanglement between any pair of spins. So any pair of the spins would be in some random ensemble of up, down, down, up, configurations. As we cool down a system, generically because of interactions, some correlated state would set in at lower temperatures with entanglement developing within the system. One simple regime of such correlations is ordering. So ordering would signal correlations setting in at low temperatures on the one hand. On the other hand, ordering also provides us handles to develop a simple low energy theory. So it's a natural place for us to start to think about material properties from the angle of the quantum information. Okay, so here are the questions I will well, the questions that motivate this work that I will be addressing in this talk. So the first question is how quantum magnetic materials, even ordinary magnetic materials such as ferromagnets, antiferromagnets, in and out of equilibrium from the quantum information perspective. And thinking along these lines, what we really want, ultimately, we want to, first of all, theoretically develop tools for calculating entanglement. But even more importantly, we want or hope that this would guide new ways to develop experimental probes to measure entanglement directly in the materials. Okay, so then hopefully this quantum information perspective will give us a new angle to think about material properties, which is complementary to the more traditional things in which you're just looking at some kind of response of a material, like conductivity or some kind of susceptibility. Nevertheless, we believe there are experimental probes which are pointing in the right direction based on optical and electrical, existing optical and electrical tools. So I'll try to mention some outlook to that end at the end of the talk. A couple questions to which our work is building up, but that goes somewhat beyond this specific talk. Can dynamic instabilities, microwave or electrically induced, the kinds of topics which are very prominent in spintronic, including a Magnon BEC that Burkhardt was talking about, can those dynamic instabilities be also offer some useful handles for tuning quantum entanglement? So first, of course, we need to be able to calculate and understand things theoretically, conceptually. But that's one experimental handle that we are intrigued. about, and in relation to that, understanding the role of dissipation in such well, in the materials, and especially driven, just in equilibrium or driven systems is very important. So whatever formalism that we're developing, ultimately it should handle these questions of strong driving, strong dissipation, and in particular, we may want to utilize some of the singular aspects associated with non-Hermitian dynamics, such as exceptional points, to tune and hopefully enhance quantum entanglement properties. So that's part of our outlook. I'm not going to talk about this today, but we're definitely thinking in this direction. And with the formalism that I'm going to discuss today, I think it will allow us to address these questions as well. Okay, so the talk is based entirely on this paper. So please, feel free to take a look at this paper if you get interested in the talk. The work was done in collaboration with my student G and Sekwon, who used to be a postdoc at the time this project was initiated in my group. He's now back in Korea, in KAIST, the University of Missouri. So this, kind of underlined, some of the key words: entanglement between arbitrary spins within the system, utilizing squeezing of magnons in order to induce and tune the entanglement, and then we're thinking and speculating about the possibility to use magnetic media. And I emphasize, for now, we're really thinking of ordinary media, nothing exotic, as a sort of a reservoir of entangled spins, which may have some functionality in quantum information. For quantum information applications, could provide you, for example, a reservoir of bell pairs, which you could use for some quantum tasks. Okay, so let me. Like I said, the talk is elementary, so I'm going to start from a very basic model from which I'm going to build up the story. It turns out this story is already quite interesting, at least for us, even starting from such a simple model of an ordered ferromagnet subjected to magnetic field. So magnetic field, let's say, is large enough that the order parameter is pointing along the direction of the magnetic field. There's a little bit of a transverse field that is tilting the magnetization, as well as anisotropy along or perpendicular to the axis, to the quantization axis, which I'm going to set to be the z-axis. So those are the three parameters that I will be tuning in the problem, while asking the question of entanglement between two arbitrary spins A and B within my material. So without anisotropy at zero temperature, for a simple Heisenberg ferromagnet, we don't expect any entanglement. So without anisotropy, the order parameter just points along the orientation of the net magnetic field, and all spins point collinearly. There will be no entanglement between any regions in your system. With anisotropy, however, the induced quantum fluctuations do result in magnonic squeezing and the entanglement, which is the main topic that I want to step through in this talk. So starting with this model, parameterized by these three parameters, we write down the Hamiltonian in the magnonic expansion to the quadratic order in magnon operators like this. So there is exchange and Zeeman term. So that would be like just an ordinary Heisenberg magnet. Plus there is there's an anisotropy term, looks like this, that is expressed in terms of magnon pair creation and the annihilation. So it looks a little bit like BCS Hamiltonian, but for the bosonic system. And we have a little bit of tilt of the magnet that, without anisotropy would really not do much, but with anisotropy we'll see an interesting interplay between the tilt and the anisotropy. So this anisotropy will control the squeezing aspect, the tilt will control the magnonic displacement aspect, and it turns out there is quite a neat interplay between the two in regard to how the entanglement sets in the system. Focusing for simplicity, for starters, on absolute zero temperature, and for starters, let's just ask what happens for a small macrospin nanomagnet. So let's neglect the finite wave number spin waves. Let's just focus on the monodomain dynamics. Already at that level, there is something to discuss. So let's start there. For the monodomain dynamics, the Hamiltonian becomes like this. We have a Zeeman a term that would govern Larmor precession, this pair production, pair annihilation term, like I said, that controls squeezing, and the magnet displacement term. So very, very elementary starting point, very simple system. Just think of it as an isotropic ferromagnetic nanoparticle that classically would undergo some elliptical precession with resonant frequency like this, where n naught here is the total number of sites. Let me suppose each site has spin 1/2, so that's the total number of individual sites constituting my Heisenberg magnet, and n that I'm going to calculate, and that's going to be an important quantity to keep in mind, is the Magnum number, which will be assumed to be much smaller than n naught for this magnonic expansion of the theory to be valid. If you have within this Hamiltonian, if we have just the transverse field in the absence of squeezing, that would tilt magnetization away from the z-axis. I'm assuming B is pointing on the z-axis, producing a coherent state with Magnum number proportional to n naught and h square, the transverse field square. If you had only an anisotropy without the displacement, that would result in a squeezed state with Magnum number given by this expression. So in the absence of an anisotropy, this Magnum number, which we'll call a squeezed Magnum number, this is the coherent Magnum number. So the squeezed Magnum number would be 0 in the absence of anisotropy. When the anisotropy is cranked up, this number increases. And when anisotropy approaches B, when the gap in the spectrum closes, this number becomes very large. Still should be much less than n naught in order for the magnonic expansion to be valid. So just quick elementary introduction about squeezed coherent states for students here. A general squeezed coherent state is written like this with respect to a Fock vacuum K 0 cat. So it could be written by displacing and squeezing the Fock vacuum. So the displacement operator looks like this. So that's just by itself, it would create a coherent state parameterized by alpha, which corresponds to the expectation value of the field operator A. And so that would just by itself, it would create a coherent state. The operator S acting on the Fock vacuum by itself, it would create the squeezed state, which is parameterized by the zeta parameter. So zeta parameterizes the amount of squeezed magnons, and applying these two operators in sequence, squeezing and displacing, you get the so-called squeezed coherent state. Okay, if you look at spin fluctuations transverse to the z axis, then without squeezing or displacing, you have some uncertainty of the transverse spin operators around 0. Of course, it should be like that because according to the Heisenberg uncertainty principle, because the operators do not commute, displacing the vacuum state simply displaces the center of mass of the quantum fluctuations while maintaining the minimal uncertainty within the coherent state. If you apply a squeezing operator to vacuum, that still maintains the overall minimal uncertainty of the fluctuations, but it increases the uncertainty along one axis and decreases along the other axis. So this kind of ellipticity, the ellipse aspect ratio of this squeezing, viewed from what it does to the uncertainty, is parameterized by this squeezing parameter zeta. So the aspect ratio of this ellipse is given by this expression. And when k is small in our model, zeta is proportional to anisotropy. If h is small, and then alpha displacement is proportional to the anisotropy. So performing squeezing and displacement at the same time, both the center of mass of the quantum fluctuation shifts as parameterized by alpha, and you get some squeezing, some elongation in the quantum fluctuations that is parameterized by zeta. Okay, so that's just some elementary primer on squeezed coherent states. All right, so let's now get to the main topic, namely the entanglement between two spins within the magnet in such a squeezed coherent state. So clearly, simply applying a displacement operator, applying the transverse field in the absence of anisotropy doesn't do anything. It's consequential to entanglement. Entanglement would be 0. Squeezing, however, does produce an entanglement which we quantify through the entanglement of formation, which in turn is quantified in terms of the so-called concurrence. For a squeezed state without the displacement, so without the transverse field, we calculate concurrence in this form, expressed in terms of it's proportional to 1 over n naught, the total sides, number of sides, times the factor that depends on the number of squeezed magnons. So like I said, if you remember, n sub s is proportional to the anisotropy for small anisotropies. When squeezing becomes large, so n sub s is much greater than 1, this concurrence goes as 1 over n naught. Most interestingly, squeezing a displaced state exhibits a jump-like behavior in concurrence. So here I'm squeezing, in this expression, I'm squeezing a vacuum state in which the concurrence will grows gently as a function of ns, starting from 0 to 1 over n naught. If you try to squeeze a displaced state, so first you displace, doesn't do anything, and squeeze the displaced state, the concurrence remains 0 up to the critical amount of squeezing, at which point it jumps in a discontinuous fashion. All right, so now I want to look at the interplay, this kind of interesting interplay between displacing and the squeezing, which I now parameterized by the number of squeezed magnons n sub s versus the number of coherent magnons n sub c. So the total number of magnons is given by the sum of these two. Again, one is parameterized by alpha, the other is parameterized by essentially the anisotropy. Now here are the plots that explain what I've just summarized in words. Here I'm plotting the concurrence times the number of total number of sides as a function of anisotropy, essentially anisotropy as a function of squeezing parameter. So in the absence of displacement for alpha equals 0, you have a sort of a gentle turn on of the concurrence as a function of squeezing. In the presence of displacement, surprisingly, the concurrence is 0 and then jumps. As you increase alpha, the critical value of the anisotropy for this jump increases. So the concurrence stays 0 longer over larger anisotropy, but then it also jumps to a higher value. If the displacement is large, the jump of the concurrence is actually twice the concurrence, the 1 over a not concurrence we get in the 0 displacement case. Okay, and in fact, this twice larger, the concurrence, this twice larger concurrence, which is 2 over n naught over here for the large displacement, is the largest possible value for the concurrence when the entanglement is equally shared by all the constituents. Intuitively, the doubling of this concurrence can be understood by as follows. In the absence of the displacement, the squeeze state involves only even parity magnonic constituents. So the squeeze state is a superposition of the vacuum state, the state with 2 magnons, 4 magnons, etc. Combining displacement and squeezing populates the ground state with odd parity components, magnonic components. So eventually, when both the displacement and squeezing are large, you end up with the largest possible value of the entanglement for equally shared entanglement case. All right, so that this plot basically summarizes. Yeah, I'm wrapping up. So that basically that gives you the gist of the kind of things we're looking at, and this, it's amusing that it becomes already, this discussion becomes already interesting even for such a simple system. If we turn on temperature, in the presence of some thermal population, it also makes sense to discuss entanglement in the Fock state, which is very similar to the entanglement in the so-called decay state and in quantum optics. Let me, I'm going to skip the details here. Just to give you just a rough idea, what is it that we're calculating? So I've summarized some of the interesting findings. The formalism goes as follows. So we're interested in the 2-qubit concurrence, which is expressed in terms of the 4x4 density matrix in this basis, up, down, down, up, down, down basis for a pair of arbitrary spins within our system. This density matrix, once we know the density matrix, then it's just a straightforward numerical procedure to calculate concurrence. In our magnonic expansion, the neat part that we're exploring is that this density matrix can be expressed in terms of the magnonic spin-spin correlators. So we're able to express this density matrix in terms of correlators, which we calculate, using standard, field theoretic tools, Wick's theorem, whatnot, and that could be expanded also to driven systems. So we can express, using fluctuation dissipation relations and things like that, we can, extend this calculation also to include dissipation to turn on things like Gilbert damping in the system. And that allows us to study concurrence with the same formalism, even in the presence of the dissipation, ultimately essentially solving LLG type of equations from which we get response functions, which then in turn through fluctuation dissipation theorem allow us to calculate correlators. So that's sort of the handle that through this formalism that allows us to also include the dissipation and even approach the physics associated with exceptional points, which could be introduced into the collective dynamics through dissipation. All right, I mean, some details, and okay, there's the last slide, sort of kind of a cartoonish conceptual outlook. So we've established that a magnetic medium, such as even a simple ferromagnetic insulator with anisotropy, provides a reservoir of entanglement. Of course, the question is that, well, we can calculate it. How do we probe that entanglement, and how do we sort of tease it out of the system and explore it? So one potential approach to both of those ends is to put integrate some external quantum spins, such as quantum dots, some self-assembled quantum dots, or envy centers. For example, this could be a pair of envy centers that you integrate with your material, for example, with some tunable exchange interaction that could be turned on and off, or some spectral properties that could be controlled on the fly, which in turn control the effective coupling of your quantum impurities with the material. So it's, in the end of the day, when you wait for some time, this quantum spins through the integration with your material, get the entanglement of the material essentially imprinted onto the spin. So for example, just as a cartoon, if you imagine as a function of time, starting with two spins in some unentangled state and turning on the interaction, and then suddenly turning it off, the entanglement between these two spins would be switched on, and after you turn off the interaction with your material, it would just stay constant. So essentially, we're proposing to imprint the entanglement on things like envy centers or quantum dots by proximity, which in turn can be sort of transfers the entanglement from your material to the system that you could now manipulate, measure using electrical or optical means. You could play additional games. You could introduce domain walls in this material to sort of guide how the entanglement is propagating, kind of enhance propagation of entanglement along certain special direction using low energy fluctuations along the domain walls. There are all sorts of spintronic tricks you could play to kind of manipulate and imprint the entanglement now on some kind of multi-qubit system that you have under control. And these centers look especially attractive to that end. All right, so that's my very simple little story. You'll find all of this, more details in the paper that I've advertised, and this is some take-home messages. We're looking at things both from the very basic perspective. We want to come up with new ways, sort of, to theoretically think of materials, as well as hopefully open new ways for new types of like really innately quantum material probes. And from the quantum information perspective, we're thinking of sort of utilizing materials as reservoirs of essentially bell pairs, which we can use for practical tasks. Thank you for your attention.